or good afternoon or good evening, depends on where you are. So my name is Yubi. I'm assistant professor at University of Rhode Island. Today I'm gonna actually host the session 3A, which is neural network on edge systems. So given that AI or neural network becomes really more and more important today, and how we actually deploy the neural network to edge devices or edge systems also become a very hot topic or a popular research area. So with that, I'll move on to our first speaker, Amir Shrativa from University of South California. So he will present the paper runtime deep model multiplexing for the reduced latency and energy consumption interface. And by the way, if you have any questions, please send through the chat so I can ask the speaker after the presentation. Okay, let's move on. Sharing.
Hello everyone, my name is Amir Shrativa. I'm a PhD student at the University of Southern California. Today I'm going to talk about a paper that I wrote with my advisor Masoud Pedram, which is
You have to unmute yourself. We don't hear you.
with neural networks.
Sorry. Okay, I have to unmute myself. Yes.
It's useful, and I will also explain what do we mean by multiplexing deep neural networks, and we will show how multiplexing helps mobile and cloud computing and their combination, which I mean we can use mobile and cloud at the same time for inference tasks. I also explain about the proposed method, which consists of two steps. The first step is contrastive learning that I will explain. What do we mean? And the second step is training of the multiplexer. And at the last part of the talk, I will show the results. So what this work is about. So this work is about how we can learn to multiplex the DNN models as a function of from small to large. And we always want to use the larger one because the larger one usually has the highest accuracy, but sometimes the smaller models can be used on some easy inputs. So the purpose of this work is to find what kind of inputs are hard for the target DNN model and what kind of inputs are easy. And the multiplexing is happening based on the input complexity. Also, the for example, exists in a cloud server or on a mobile device, also plays a factor in this multiplexing decision. So the feature of our multiplexer is that it has little overhead because, as you can imagine, we are running another step on top of a typical inference task, which is the multiplexing itself, which can be seen as a pre-processing on the inputs. So we apply this pre-processing on the inputs, which should have little overhead to achieve like lower latency or lower energy consumption. So this approach enables the mobile devices to perform the easy inference task locally and offload the hard ones to the cloud server. This means that the privacy of the users are somehow kept on at least the inputs which are easy, and they are not needed to be always floated to the cloud servers. So another aspect that our approach can help is the cloud intelligence services, which can benefit the cloud providers by instead of actually replicating the best performing model, they can host a range of models from small to large sizes, and they can choose which model they want to use for the inference task. So you can choose the smaller models for the easy inputs, and you can choose the larger models for the hard inputs. So the cloud doesn't need to always host the most complicated neural networks. It can also host smaller ones, and it will be beneficial for the cloud server, as you can guess, because they are saving their resources. So what is the status quo of current AI in the mobile and cloud computing scheme? So assuming that we have a small model, then we can host it on the device. So the whole inference is done on the mobile, and nothing is uploaded to the cloud. On the other hand, if we have a large model, then we cannot host it on the mobile because the model is very large and the mobile cannot do the prediction tasks in real time. So we host the large model in the cloud server, and we send, actually the mobile sends the inputs to the cloud server, and the cloud server returns back the predictions on the inputs that are sent by the mobile. So in this scenario, for example, the inputs are always uploaded to the cloud. So we show how multiplexing the easy and hard inputs can look like in this image. So assume that we have two models. One model is a small model which is hosted on the mobile device, and the other one is a large model which is hosted on the cloud server. We designed a model multiplexer which takes the input and decides whether the input is easy or hard. If the input is easy, then the inference is done on the mobile, and if the input is hard, then it is sent to the cloud for the prediction, and then cloud sends back the result to the mobile. In another scenario, suppose that you are a cloud provider and you are providing some API for the users to do some prediction task. So assuming the current status quo in the cloud servers is that they replicate the best performing model, and they use the best performing model for all the queries. But as we show, we can choose which model we want to do the inference, because if the input is easy, then using a large model is just a waste of resources. So what we are looking in this problem is actually the task of predicting the predictions, because we want to know which model will fail in the prediction or which model will be successful in the prediction. In this figure, we have shown the TSNE visualization of the feature space of 6 benchmark DNA models, and the red dots in these figures show the embedding, like the embedding point of the incorrect prediction, like the model has predicted the label incorrectly. And the blue ones show the correct predictions. As you can see in this image, they are overlapped. They are highly overlapped, and finding a separation between the correct prediction and incorrect prediction is hard. So what we are proposing in our work is that we are looking for a target embedding space that looks like the top image. So as you can see, the embedding space of 3 models are shown here. So the gray region, which represents model 1, model 2, and model 3 means that all the 3 models can predict those inputs correctly. And then, for example, the red region, which only is for the model 1, means that those inputs can only be predicted correctly by model 1. So our target embedding space looks like this, which we are separating the expertise domain of different neural networks. And on the bottom image, you can see our resulting embedding space as we wanted in the top image. So on the left, you can see the embedding space of two models for the mobile cloud computing scenario, where we have a mobile which wants to offload the hard inputs to the cloud. So the mobile net V2 is the model that is hosted on the mobile, and the ResNext 101 is the model hosted on the cloud. And you can see that the embedding space looks like a Venn diagram. On the right, you can see 6 benchmark DNN models and their embedding space that are the result of a training method. And you can see they also are close to a Venn diagram. So how did we achieve that embedding space that looks like a Venn diagram? So it has 2 steps. The first step is learning the models using our proposed contrastive loss. In the contrastive loss, what we want to actually do is that we increase the distance of the embeddings of 2 models if one of them can predict the input correctly, and if the other one cannot predict the input correctly. And we decrease their embedding space, their embedding distance, if both of them can predict the input correctly. This is what we have shown in the second equation here in the contrastive loss, where D represents the distance, which in our case is the cosine distance. And you can see that the loss function in the contrastive loss has a positive sign for the case when the outputs, that when both models can predict the label correctly, and it is negative when only one of them can predict the label correctly. So what it does, it tries to create that Venn diagram that I showed in the previous slide. In the second step, we transfer or distill the learned embeddings into the multiplexer. So the learned embeddings are separable, so they form in a space like a Venn diagram, so they are easily separable and they can be easily learned by our multiplexer. So the multiplexer takes the embeddings that are learned using our contrastive loss and tries to learn the multiplexer in a way that it also captures the computation costs that are related to, for example, how much compute resources and one neural network wants, and how much resources another neural network wants, and decides which neural network is beneficial for us to use based on the cost that we want to spend. The results of our approach is shown here for the mobile cloud collaborative inference, in which case we have a mobile device and the cloud server and offload the hard inputs to the cloud and do the easy inputs on the mobile side. So as you can see, the latency and mobile energy consumption has increased in comparison to the mobile-only approach, but it has decreased compared to the cloud-only approach. So this means that if you want to achieve cloud-level accuracy with lower latency and energy costs, we can use our approach, which is about multiplexing the models. So in our hybrid approach, 68% of the inputs are processed locally on the mobile side, which means that 68% of the inputs are not uploaded to the cloud. So the privacy of the users is somehow kept for at least 68% of the inputs. And the accuracy that we achieve is also increasing because the mobile-only and the cloud-only expertises can be adding to each other, and it also leads to a higher accuracy. Also, the results for the cloud-based API inference is shown in this table. we have used 6 benchmark DNNs, and you can see that it also leads to improved accuracy and lower latency and lower floating point operations compared to the deploying the best performing model and replicating the best performing model. Our approach is more efficient. Thank you. This is the end of my talk.
Okay. Do you have any questions? Amir, can you unmute yourself if you are here? Okay. I think he's probably not here. Okay, let's move on to our next speaker. Okay. Matt Pantho from University of Florida. He will present the paper near sensor interference architecture with region aware processing.
My name is Pantho. The paper I'm going to present today is near sensor inference architecture with region-aware processing. The authors of this paper are myself, Pankaj Bhumi, and Christopher Bobda. We are from the EC department of the University of Florida. These are the content of my today's presentation. Convolutional neural networks have been adopted in a wide range of vision-based application domain in recent times due to their success in enabling ubiquitous machine vision and intelligent decision. The exceptional performance of CNN in computer vision application has seen growing interest in developing hardware accelerators for deep learning algorithms. These architectures typically employ a large number of math units, but vary significantly in the interconnection network, memory hierarchy, and data flow. In the conventional approach, the sensor acts as a pixel acquisition unit and transfers raw pixel to a memory or a processing unit for further processing. In these systems, the pixel data transportation time between the pixel acquisition system and the high performance accelerator remains a bottleneck. Moreover, all pixels in the sensor are treated equally and non-relevant pixels are transferred regardless of their importance, which worsens the bottleneck. To this extent, deploying CNN directly on the sensor can avoid data transmission latency, minimize the bandwidth of sensor-processor communication, and alleviate the burden imposed on the back-end process. Besides, if we can limit our processing to relevant regions, greater performance can be achieved. Here we present a novel approach to integrate a CNN model near the sensor with the pixel parallel setup. The main contribution of this paper are we propose a hardware model to enable CNN inference near the sensor for different vision application. We present an attention-based hierarchical processing model to reduce computation burden and improve power efficiency for pixel parallel processors. And we adopt a suitable communication structure for pixel data propagation to minimize interconnection. In our architecture, we map the sensor pixels to an array of their parallel processors. The proposed design considers a standard imagery depicted in the figure, where each sensing unit in the photodiode array has an analog to digital converter and a local memory. The imager is coupled with two inference computation layer, ICLC1 and ICLC2, to perform inference near the sensor. The acquired image pixels at the sensor are transferred to an output pixel buffer OPB for further processing by the ICLC1 layer. In ICLC1, the incoming image frame is logically divided into m image regions, and for each region we have the RQ assigned to it. The ICLC1 layer directly operates on the incoming pixel to calculate the first convolution layer output of the CNN structure, while ICLC1 layer works on the output of the ICLC1 and perform computation for the consecutive layers to generate output. Here we also have a controller that acts as a control unit and is responsible for maintaining the coherency between the different layers of the architecture. The unit acts as a custom scheduler that keeps track of the output feature maps in the ICLC1 and ICLC2 level processors and govern data flow from one layer to the next. The computational layer operates in a unified framework to realize a high-level application and can be repurposed for a different scene and application. To reduce interconnection, we have one pixel streaming channel per region between the output pixel buffer and the ICL layer. These streaming channels can stream pixel values for different image regions in parallel. The RPUs in the ICLC1 receive pixel data from the OPP in parallel, where each RPU receives the pixel associated with the region sequentially. Each PPU locally stores its neighboring pixel values required to perform convolution and forwards other pixels. The PPUs are the building block of our design. The PPUs are specially designed to perform convolutional operation and are highly optimized to hide latency and to reduce external memory access. The neighboring PPUs in the ICLC1 and ICLC2 layers are designed to perform convolutional operation on adjacent pixels that have overlap within their kernel region. Each PPU has an attention module and a vector MAC unit. The attention module calculates the relevance of that pixel, and the vector MAC unit is responsible to calculate the convolution operation of that pixel. Each pair of PPU along the row share their weight and pixel buffer. The pixel regions differ between two row-wise neighbors by one column of pixel for a stride size of 1. So for this case, the sharing of weight kernel is straightforward, whereas for sharing the pixel values, we arrange the pixel values column-wise in the shared pixel buffer for easy sharing. As I mentioned before, we have an attention module integrated in each of the PPU units. The attention module calculates the predictive coding in space for each pixel by using the equation over here. Here we try to predict the center pixel from a weighted average of neighboring pixels. If the prediction is correct, we send an error bit of 0 to the RPU, and if the prediction is incorrect, we send an error bit of 1 to the RPU. If the number of mismatch received in the RPU is greater than some threshold, we depict that region as an ROI region. Whereas if the value is less than some threshold, it's a non-relevant region. What we do over here is, if a region is non-relevant, for that region, we do not active the region processors over there. If we only active a region if the predictive coding and space and the predictive coding in time for that region corresponds to 1. Here for MNS dataset, we divide the image into 16 regions, where each region has 8 × 8 pixels, and we simulated the design for different threshold values. As you can see, for in the RPU, if we assign a threshold value of 5, we can have almost 50% of the region inactive for most of the cases, whereas the accuracy remains as high as possible. Next, we evaluate our design by implementing it on Vertex Altesco class FPGA using Vivado Design Suite 2018.2. While developing in the FPGA, we emphasize on reusing the RTL design in ASIC. We simulate our architecture with different region sizes for an image size of 32 × 32, which is MNIST dataset image size with padded 2 padded pixels. The region size of each RPU is a design choice, but we notice an increase of area overhead and latency with the increase in region size, but the number of interconnection decreases. We designed our ASIC design with TSMC standard cell library for 90 nanometer technology. Here we can see that we have a leakage power of 14.2 milliwatt for one RPU in the ICL layer. Architecture-wise, the RPUs in ICLC1 and ICLC2 are almost similar, with a slight difference in the weight buffer size and pixel buffer sizes. We report a maximum frequency of 480 MHz in FPGA and 500 MHz in ASIC. Next, we exhibit
hi, Dr. P. I think there's a problem with the sound.
Power if the region of interest is less than 87% of the image frame. Next, we show the pipeline architecture of our design. We designed the pipeline architecture in such a way that the moment the first PPU in the ICLC1 layer receives all its pixels, it starts computing the convolution layer for that pixel. And the moment the first ICLC1 layer computes the first output feature map, that feature map is transferred directly to the ICLC2 layer, and the ICLC2 layer starts processing. In our architecture, ICLC1 starts processing on the 17th clock cycle and ends at 135th clock cycle. We present a near census CNN inference in this paper that enables a reduced number of execution. The attention module determines the ROI and ensures the ROI RPUs are triggering to initiate CNN processing. The proposed method offers massive parallelism, pipeline execution, and efficient weight management system by storing weights locally.
Okay. So any questions to Matt Pantho? Matt Pantho, can you unmute yourself?
Yes, I am unmuted.
Okay. Our audience, do you have any questions for this presentation? Okay. I have a question to ask, actually.
Yes,
so
sure.
how does the attention module works?
So the attention module works in a distributed manner. So we divide the region into a set of image patches, and for on each image patch, for each pixel, there is an attention module that computes the predictive code that tries to predict the center pixel of that center pixel from the neighboring pixels. If the prediction is correct, that means we are actually relying on a homogeneous region, at least for that pixel. And if for that region we have too many number of pixels which can be predicted from its neighbors, we can safely assume that this region is close to a homogeneous region. And for the attention model, what it does, if for incorrect prediction, it creates a single bit of error, and this single bit of error is sent to a local processor for each RPU. For each region, and the RPU for that region counts the number of mismatches. If this mismatch is greater than some threshold, that region is identified as important region, or otherwise that region is identified as non-important, and the whole RPU region and all computation unit within that RPU region is turned off for that particular frame.
Okay. Okay. Thank you. Audience, do you have any questions? Okay, thank you, Matt. So let's move on to welcome our third speaker, Jiangsu Du from Sun Yat-sen University. He will present the the paper distributed in situ CNN inference system for IoT applications.
Everyone, I'm Jiangsu Du from Sun Yat-sen University. I'm going to present our work, a distributed in situ CNN inference system for IoT applications. Having limited computation and storage, most IoT devices are not capable of hosting the compute-intensive CNN inference. Today, the cloud-based method is widely used. However, it heavily depends on external infrastructure and sometimes faces the privacy issue. Okay, let's focus on the in-situ deployment. Besides adding AI accelerators, we can distribute the workloads over local devices. However, it's hard to distribute the inference of existing CNN models. A CNN model is made up of multiple kinds of layers, and these layers connect in series. Here, we mainly introduce convolution layers. It consists of input feature map, kernels, and output feature maps. A kernel slides over the width and height dimensions of the input feature map and produces a channel of output feature map. Notably, the kernel and the input feature map have the same number of channels. To distribute it, existing study partitions convolution layers through width and height dimensions. And each device needs to keep all kernels in memory. When the width or height of kernels exists 1, there requires communications. Besides frequent communications for removing data dependency, the network connection is weak in the context of IoT. Latency can range from 1 millisecond to 20 milliseconds or even worse, and the bandwidth is also very limited. Generally, the time for latency rather than the transmission time dominates the data delivery time. We propose 3 techniques and implement a prototype system for distributed in situ CNN inference. The first technique, LCS, is motivated by the investigation that existing CNNs are tightly coupled. We design LCS, targeting both the loosely coupled structure and the leading efficiency. The second technique, SOP, partitions LCS with as fewer synchronization points as possible. A synchronization point is a place where requiring communications when distributing. The third technique, DAC, focuses on optimizing communications of synchronization points. To design a loosely coupled CNN model, we are mainly inspired by AlexNet. It adopts group convolution and distributes onto 2 GPUs for training. Group convolution is a variant of normal convolution. The input feature maps are evenly grouped, and each kernel only operates on input feature maps of a group. The output feature maps, input feature maps, and kernels within the same group are completely independent of other groups. We propose 2 design ideas, the homogeneous group and the intermittent shuffle. The homogeneous group uses group convolution in the convolution layers. We select 2 efficient settings of group convolution. The first one is the point-wise group convolution. Its width and height of kernels is 1. The second one is a depth-wise separable convolution. Its number of groups is equal to the number of channels. We connect them in series to ensure the loosely coupled feature in the main branch. When the thread is 1, the residual branch is a copy, and we merge it with the main branch by add operation. When the thread is 2, the residual branch is the DW_conv and PG_conv, and we merge it with the main branch by concatenation operation. Besides, the output of the main branch is each channel group must add or concatenate with the output of the residual branch in the related group. Next, already with basic units, we follow the intermittent shuffle to establish the entire model. Channel groups of 16 basic units are totally independent with each other. Using different parameters, the computation amount of LCS is scalable, and this figure shows the LCS1. Generally, the larger the computation amount, the higher the accuracy. However, since there lacks information exchange between channel groups, the model accuracy is seriously hurt. The intermittent shuffle inserts channel shuffle operation between basic units. Channel shuffle divides each group of input feature maps into subgroups, and each kernel in the layer is fed with feature maps from different groups. Our experimental results show that only a very limited number of channel shuffles is adequate, and more channel shuffles will not bring accuracy improvement further. For LCS1, 3 channel shuffles are enough. Based on LCS, SOP includes the partitioning methods for convolution layer and fully connecting layer, respectively. Since there is completely no data dependency between channel groups, we partition different channel groups into different devices. Compared with previous methods, each device only keeps related kernels in memory. For fully connected layers, the weights related to the same input neuron are allocated to the same device. It has less communications and less data transmissions. Based on LCS and SOP, synchronization points are largely reduced compared with previous methods. DAC aims at optimizing communications for remaining synchronization points. At first, the asynchronous communication is used to overlap communications. The master-slave pattern requires 2 rounds of communications, while the decentralized pattern requires 1 round, largely reducing communication overheads. Further, we abstract our system into 3 modules. The launch module, which for launching the execution on other devices. The execution module for performing operations of CNN inference. The communication module for communications. To show the effectiveness of our system, we first compare LCS with other popular CNN structures. From the table, the previous CNN structure, VGG16 and ResNet50, achieves a similar top 1 accuracy with much larger computation amount. Next, we visualize the results of ShuffleNet, MobileNet, and our LCS. From the figure, we can find that LCS can achieve the leading accuracy under a given computation budget, compared with other leading structures. Then we analyze the overall performance. At first, the blue line in the left figure shows that as the network condition goes weak, our system can effectively distribute LCS2 over 4 devices. The performance is not very sensitive to the network condition. For LCS1, since it is so tiny, computation time only takes a small proportion compared with the communication time. In the right figure, as the network condition weakens from left to right, the speed up reduces a lot, approaching the single device inference. Thus, it is more beneficial to adopt distributed inference in high accuracy models. Then we compared our system with other approaches. It is obvious that as network condition goes weak, our system shows a much better latency result compared with the other combination of CNN structure and partitioning methods. For memory footprint, since each device only requires to keep part of kernels, and other approaches need to keep all kernels in the memory, our system has the least memory footprint in each device under a given computation budget. Here comes the conclusion. In short, we advance distributed in situ CNN inference from not only system, but also from CNN structures. From the CNN structure perspective, we propose a loosely coupled structure with leading efficiency, reducing data dependencies fundamentally. From the system perspective, we study both the partitioning method and the communication method, achieving good results on both latency and memory footprint reduction. That's my presentation. Thanks.
Okay. Our participants, do you have any questions for Jiangsu? Jiangsu, can you mute yourself? Unmute yourself.
Oh, hi.
Any questions?
Can you hear me?
Okay, I do have one quick question. What's the data transmission amount compared with the other approaches?
In the paper, we demonstrate that the time for latency rather than the data transmission time dominates the communication overhead. Actually, the data transmission amount is related to the place where channel shuffles are inserted. And there are some methods to determine the place. In particular, under our experiments, the data transmission amount using our approach is similar to other approach. Yes.
Okay. Any questions from the audience? Okay. Thank you, Jiangsu. So let's move on to our fourth speaker, Xiaozhong Luo from Nanyang Technological University. He will present the paper EdgeNets, Discovery Efficient Neural Architecture for the Edge Systems. Okay.
My name is Luo Xiangzhong, a second-year PhD student from Nanyang Technological University. Today, I will introduce our work, which will appear in the International Conference on Computer Design 2020. It is EdgeNets, Discovering Efficient Neural Architectures for Edge Systems. You know, I have only 10 minutes, so I just briefly go through our work. So if you are interested, you may refer to our publication for more details. Here is the main content for today's presentation. At first, I will give the background of our work and then provide a motivational example. Then we will elaborate on our proposed EdgeNets framework, followed by the experimental results. Here, the proposed EdgeNets is to automatically design hardware-efficient neural networks, like with low latency, low memory footprint, or whatever. In this slide, I will briefly introduce DATS, which is our baseline framework. Here, DATS means differentiable neural architecture search. In DATS, we aim to search for a computation cell, which is something like a microarchitecture, which can be stacked sequentially by several times to construct the final neural networks. Before we perform the architecture search, the operation in each edge are not determined. To begin with, we initialize one over-parameterized cell, like figure B. It consists of two types of parameters, like the network weights and the architecture parameters. Here, the nodes, like node 1, 2, 3, they denote the intermediate feature maps, and the colored edge between two nodes are the operations, like convolution or pooling or whatever. Finally, we can derive the searched cell, like figure C and figure D, by sampling the most capable operation in each edge in terms of the architecture parameters. Intuitively, architecture parameters denote the probability, like the strength of the corresponding edge. Finally, only the strongest edge will be included. Here's the optimization objective in DATS. It involves a bi-level optimization program, like you first fix the architecture parameters and then optimize the network weights. And next, you fix the network weights and then optimize the architecture parameters. So you can see it only focuses on the accuracy and cannot optimize the efficiency. So usually it derives complicated neural networks and cannot be efficiently deployed on resource-limited edge systems. Here we show our motivational example. Previous works usually use flops to denote the complexity of designed neural networks. However, flops cannot directly translate to the runtime performance, like latency. Here we sample a set of architecture candidates from our search space and then show the relationship between flops and the runtime latency on our edge system. So you can find new architectures with the same latency are significantly different in terms of the flops. So flops is hardware agnostic. So now we come to detail our proposed diagnostic. Here we give the overview. There are two key components, like first how to efficiently and effectively obtain the runtime latency, and then how to incorporate the latency to guide the architecture search along the low latency direction. Since the search space is quite large, we cannot measure the runtime latency for every architecture candidate on our edge system. It is really time consuming. So we first introduce a latency predictor to quickly obtain the runtime latency. And then we incorporate the latency predictor as a latency regularizer to guide the architecture search. And next, we will introduce our proposed latency predictor, which is simple but effective. And remember, between each two nodes, only the strong stage will be reserved, while others will be excluded. So here we can binarize the architecture parameters using 0 and 1, and this will be a unique representation. And then we build an MLP-based neural network and use the previously sampled architectures to train this latency predictor. Here is the predictive results. So you can see the latency predictor can accurately predict the runtime latency on our edge system. However, directly incorporate the latency into the supernet training will make the architecture search biased. So here we use a uniform sampling strategy. We first generate multiple masks and then mask the architecture parameters to generate multiple architecture candidates. So next we can use the expected latency of those new architectures and then incorporate it into the training loss function. Here the beta is the trade-off factor between accuracy and latency. The key point behind the dots is differentiable. So next we can get the gradient following the chain rule. In this way, the architecture parameters can be updated along low latency direction during the gradient descent. By incorporating the latency regularizer, the proposed diagnostic is able to explore the resource-efficient new architectures, but we observe AgNAS tend to select computation-free operations like skip connect to improve the efficiency of the search architecture. But too many skip connect operations will significantly hurt the accuracy, like with bad generalization. So here we introduce a constraint, like the architecture search will stop when there are 2 or 3 skip connects in the normal cell. So this will generate 2 search patterns, like 2 skip connects as the mild search pattern and 3 skip connects will be the aggressive search pattern. Next, we will demonstrate the experimental results. We perform intensive experiments on 3 benchmark datasets, like Cepha10, Cepha100, and ImageNet. Here is the searched new architectures on Cepha10. The left is the mild, and the right is the aggressive. And next, we directly evaluate the searched architectures on Cepha10 and Cepha100. So we can see the new architectures searched by AgNAS can achieve higher accuracy, but with low latency. And besides, the search cost can also be reduced. Next, we transfer the searched architectures on ImageNet. So you can see the new architectures searched by AgNAS can achieve comparable accuracy but with low latency. Next, we explore the impact of different trade-off factor beta.
Okay. Our participants, do you have any question for Xiangzhong? Xiangzhong, can you unmute yourself?
Oh, yeah. Can you hear me?
Yes.
Okay, thank you.
Okay, Xiangzhong, I do have one question. So in this work, you only consider to optimize the latency. So how about the other like metrics, such as power consumption?
Oh, yeah. Since there are so many like the performance metrics on hardware, actually we also consider to incorporate the power consumption. But the power consumption, we need some like the power meters to measure the power consumption. And currently we do not have those power meters, but actually this will be our future directions.
Okay. All right.
Oh, yeah.
Okay. Thank you. Thank you all the 4 speakers. It's a really nice presentation, and I think we run out of time. So this will end our session 3A. I'll pass it to the next host. Thank you all.